Good morning, everybody, and thank you for attending my presentation today on a vision on the estimation of photosynthesis active radiation fapar using sensor networks. Buenos días a todos y gracias por venir a mi presentación. Bon dia, and let me give my talk in English, and at the end, if someone has questions in Spanish, we can always answer them. When I was trying to put together this presentation, the first thing that came to my mind is the challenge that we face in terms of environmental monitoring. And basically, we're doing with three main things. The first one is that our science, or the way that we do business, is evolving as technology evolves. And with that evolution, we are requesting, or we have to confront the need of conducting a new synthesis with more and more data. And that's one of the challenges that we're facing, is the disproportionate increase in data availability. And what we ask ourselves every day is, how am I going to manage this amount of data? How can I going to analyze it? How am I going to be able to visualize terabytes of information, especially in the Americans, when we see more and more, for example, carbon flux systems going up, etc. How are we going to be able to visualize all of this at the same time and then make decisions or understand the data that can help us to communicate and this to the policymakers? And the fundamental question at the end of this is, how do we accurately communicate environmental trends using clear language when we have to integrate new synthesis and when we have to manage, analyze, and visualize terabytes of information? So this kind of environmental challenges that we are facing today as a scientist do not come out of the blue. They are a process of evolution. And I think that they are associated to the evolution of scientific paradigms. Jim Gray from Microsoft published a book called The Four Paradigms of Science. And basically, he explains the evolution of science from being empirical, starting a few thousand years ago, to the second paradigm of science, when we have science that was more theoretical, like Newton and the force equals mass times acceleration. And when we develop models and generalizations and so forth. And then these two elements, these two pillars of scientific knowledge evolved into a third paradigm at the late 1940s, 1950s, when the development of the first computers. And at that time, we were able, as a scientist, to do more advanced simulations of complex phenomena. And everything evolved in the last few years. And today, with the evolution of the fourth paradigm of science, or what we call e-science. And it's more like a unifying theory where we have experiments, simulations, and then behind that, we have elements of analytics. And it's in this paradigm when we're facing that challenge of more data, more visualization needs, and the need to bring all of this knowledge into the process of policymaking. So when many years ago, when we start facing the need to working with fapar, we start facing the issue, how are we gonna handle this? How are we gonna do that? And working with we found out ourselves that we were either third paradigm and touching in the fourth paradigm a little bit. But we were still a lot in the third paradigm. There were some things that they were emerging, but even when you talk to vendors 10 years ago, they say, well, Arturo, this is something out of a Hollywood movie. But there was that kind of element of evolution. And what is basically happened is that a few years ago, with the technology development, our system became smarter. We were able to develop more advanced instrumentation. These instruments allow us to interconnect in a way that we can develop monitoring systems that allow us to do, for example, essential climatic variables at a very high rates and combine. We can measure in the same sensor temperature, relative humidity, photosynthetic active radiation, and so forth. But if you look at a few years ago, this was done individually or with a very large data loggers. Right now we have small data loggers that can do things like that. So it allows the interconnectivity. And when we have instrumented sites, when we have monitoring systems that are interconnected, and we have intelligence associated to this, in how we deploy the networks, in which direction, at which height, etc. And how we integrate vegetation and structure, for example, what we are getting is information that is smart. So I see it as an engineer, as a tool for better operations associated to environmental monitoring, and can allow me to better understand the process. So in that regard, if I have systems that are instrument, interconnected, and intelligent, I can make smarter decisions. So I got very interested in the fraction of photosynthetic active radiation because it's a very interesting variable that can be related to the amount of light that the plants use for photosynthesis. And it can be related to ecosystem health. It also can be related to droughts. And since I work in tropical dry forests in northwestern Costa Rica lately, to me, it presents a very interesting opportunity to actually look at the effects of climate change. The problem was that this is the best that we could get at the time. This is a modest fapar, and you start wondering, is this good or bad? How can we validate this? What can we tell us 8-day data or 14 days data? When in the case of Costa Rica, if it rains, the trees can cover themselves and leaves in less than 9 days. So we needed to start thinking about very closely about how can we measure fapar? And some initial studies by some scientists in the United States and so forth usually deal with one sensor or one row of sensors. And we were dealing with the need to have par. And how can we actually develop that vision? The vision comes from incoming par that is measured in the top of the canopy, and that par comes through the canopy, and there should be a net of sensors that collect that information. And so we started developing that concept with some colleagues in computer science and electrical and computer engineering, in which we have small systems. And this is when a lot of comments and questions start coming out. Phenology plays a very important element. How can we deploy sensors? What is the distance between sensors? What kind of geometric pattern do we have those sensors? But actually, at the end of the day, there are even questions more basics than that. Is how can provide enough energy for those sensors to run? What kind of batteries do we need? How they communicate? What kind of protocols? And also, how do we send information from a node that communicates with an aggregator to either by satellite or by phone into a system that can allow us to see information in real time? None of this existed, and we have to do a lot of research with many colleagues. And after many different types of experimentations, we got our first system deployed. This is how it looked. This is what we call the yellow box wireless sensor network that had the capacity to measure photosynthetic active radiation, temperature, relative humidity, and soil moisture. And we start deploying them in our different sites around the world. Another question that came across is, how do we deploy them? What kind of geometric pattern? And I think that this is very interesting because some people was interested in transects, concentric around a tower, or grids. But at the end of the day, we are trying to cover as much possible space. And if you have a flux tower like this one that we have in Rue, I think that got burned a few years ago. in South in Victoria, in Australia. We wanted to have the footprint of this fully covered. And working with our colleagues in computer science, we came out with this idea of developing a hexagon a deployment, and which basically allows for maximum coverage in terms of signal, and it prevents overlaps. So we were actually trying to think about ways where the data, that the light that we were looking at was independent, and we didn't have a special autocorrelation between these. Now, the distance between these, it requires some studies in its ecosystem structure, and using some terrestrial laser scanning to understand light distribution. But I think that in that regard, I think that we did a very interesting approach. And then it came the need for visualization. And we have a few attempts to do that, and we developed EnviroNet, which basically allows us to visualize, retrieve, upload, and manage wireless sensor network information. So this is a process that took about 20 years, I think. And it starts with the process of concept development and of a sensor, the analysis work platform, how it's going to look, how it's going to be able to handle the data. Our first option was to develop a black box, and even the winterizing of what we call winterizing is how to deal with a box that can actually be left in the snow in the Arctic, or it can be left in a place in Costa Rica or Panama with a high moisture and high temperature. So we started about during 2004 and 2006 with this process, and then around 2006 we did our first initial deployments in Brazil and Australia, and we deployed the yellow box there and the EnviroNet box. And then came an international expansion of the work that we are doing with sites across many sites in the Americas, Australia, Germany, the UK, and Singapore. And today what we are doing is we are trying to refine this analytical component. So in order for us to develop better tools for environmental monitoring in real time. So this is one of the sites where we originally started working. Most of these were the testing sites, like the ones in Argentina, or site in Chemela that was destroyed by a tropical storm. But we have two sites that are fully operational right now. It takes time. One is in northern Alberta, the Peace River Environmental Supersite, and the Santa Rosa National Park Environmental Monitoring Supersite, which is going to be the one that I'm going to use for this talk. And this is it. The Santa Rosa site is located in northwest Costa Rica. This is a site where we are conducting a significant amount of work in fapar and also carbon fluxes. I don't know if it's probably one of the few sites in the world that has in a very small area 3 carbon flux systems and a very large wireless sensor network that allow us to understand essential climatic variables associated to carbon fluxes and then associated to phenology. The distance between the towers is about 1 kilometer between them. And basically what we're trying to do is to understand the elements of variance in carbon fluxes. So it's a very interesting initiative that we are trying to put together and maintaining for the next few years. So basically what we have in Santa Rosa is a set of nodes that you can see in blue. And then we have the green aggregators that collect information from the nodes, and they transmitted this to a site where, let's see, sorry about that, a site where the data is sent via cellular phone to the EnviroNet at the University of Alberta, and from then it goes into the visualization tools that we have and the analytics tools that we have been developing. And this is some of the examples. I think that's one of the most interesting things is how wireless sensor networks can help us to validate satellite data. And as I mentioned at the beginning, one of the main interests in this was how good those softwares and platforms that provide us fapar for like sensors like MODIS or Sentinel-2 are. And that this is a clear example. You can see here the two flux a wireless sensor network fapar for the Santa Rosa National Park is about 35 nodes providing information aggregated, and then this is the measurements from the Sentinel-2. So what we are observing is that at least with this specific data set, Sentinel-2 is underestimating the amount of fapar that we are estimating. The same thing can be said about MODIS fpar versus in situ fpar. And in some sites, in some seasons, the difference can be up to 41% in between the observed one and the mean observation using Terra or Aqua. So there are good days and there are bad days, but difference can be significant. Sometimes it may look like you are measuring a different site. And in many cases, the errors are associated with the algorithms that MODIS fapar uses. For example, they use lookup tables and the dependency on NDVI. One of the things that we found more interesting, and I think that has been the outcome of looking at our wireless sensing technology and micrometeorological variables, is the impact of fapar, the WIN, on fpar estimations. And you can see right here, and this is a paper by Brigitte Purnes. She published 3 papers on this eventually, her doctoral dissertation. And as you can see, this is WIN at the bottom and this is fpar at the top. The bias of fapar increases after the speed. The WIN speed is 5 meters per second. After 5 meters per second, there is a lot of high level of variability on fapar. And basically what is happening is, if you imagine the leaves tremble like this, and basically what it does is creates a very random light fields. So it's very difficult to estimate an accurate value of fpar. And but if you look at the speed between 0 and 5 meters per second, you know that more or less you are stable. So this is something that people have not considered before, and that we always think that it's important for part of our vision that we have to take into consideration with spin when we look at fapar measurements. So what the future holds in all of this? I mean, we have been developed the technology, we have a platform. What do we understand about all of this? How can we put it together? And I think that to me, the first one is to actually look at micro events that we would not be able to look before. And it provides a very interesting understanding of ecological processes. This is, for example, from a wireless sensor network in Brazil. And if we actually, you look at normal year, it will have the dry season, and then it starts raining, and then the leaves are covered with, the trees are covered with leaves, and then we will go all the way, and then it starts the dry season again, and then it comes all the way down. Now, in this specific year, the following year, we have a significant storm, and we were able to characterize the effect of the storm on fpar. And you can see right here, it starts in the normal conditions, and we saw this effect. So we can actually compare the year before and the current year, and we can see that there is a significant loss of productivity as a result of the storm when we can use fapar and wireless sensor network. So the storm happened here, and you can see the effect. Another element that we were looking at is this. And in Costa Rica, one of the things that we thought that these events are is to droughts in the middle of the rainy season. And in truth it is, but in the case of Brazil, it's not, because they don't have droughts in the rainy season. This is insect attacks. So basically what they do is make holes through the leaves, or eat the whole leaf, or create a lot of leaf holes, and you have more light reaching the bottom. So there is more transmittance. And what happens is after a while, all they eat as much as they can and the forest recuperates. So this is an element of an instant act in an area that is monitored by one of the nodes. If we didn't have that, we would never detect it. So for us, it's a very interesting opportunity to understand ecological processes like a herbivore against the effect of an ecosystem to light. Another one that to me is more interesting also as well is the role that lianas, and how can we separate the ecosystem? When we look at the essential climatic variables in the tropics, we always focus on trees, like if the lianas do not exist. And you can see in this specific photo here, there is a significant amount of lianas. They go all the way to the top of the canopy, put the leaves there. And in the rainforest, it's very difficult to characterize their impact. But in the dry forest, when we have learned the lianas keep the leaves longer because they have deeper roots, we can actually look into the lianas. Why the lianas are important? First of all, they are parasitic elements, and they are linked to climate change because there have been some studies that suggest that lianas are increasing as a result of climate change. They tend to suppress tree regeneration and affects the recruitment in secondary growth forests, and can arrest succession, can affect the process of ecological succession. And finally, some papers are suggesting that between 43 to 86% of all trees in the tropics have lianas. So the problem is that we forgot that they exist, but they are there. They are not going anywhere. So what is the relative impact? So in the future, this is, for example, some of the experiments that we have between non-liane infected sites and infested sites. In blue, there's the infested sites, and red is the non-liane infested sites. And we can see that, for example, during the senescence part of the year, there is about a difference between 3 to 37% in fpar. And during the rainy season, when you have full leaf coverage, that difference is very small, it's 4 to 8%. Now, what is very interesting here is that this shift that we see right here is the result of liana holding leaves longer into senescence. So in many cases, the outcome of this is that the remote sensing product is not bad. It's actually detecting lianas, and we think that there are trees, which in fact is not. We can see it very clearly that the lianas keep longer their leaves. And it's probably one of the things that comes across as a very interesting opportunity for research on this. So some final remarks for us to think about it is how can we start integrating our work on the emerging scientific and technological paradigms that are evolving. I think that there is a tremendous opportunity when we start looking at essential climatic variables and fpar. And that when we start looking at this, we need to think about what will be the future. Ask ourselves, where do I want to be in the next 5 to 10 years? What kind of a scientific development do we want to keep up in mind and start working towards that? In the case of specifically of the wireless sensor networks, we can see that having a vision like this can help us to better understand remote sensing algorithms, see where they are failing. Because we cannot, everybody talks about NDVI, validation of NDVI, but nobody talks about the validation of other products. So we take them for granted. And it's not true that we have this kind of information there. And finally, we need to start looking at other components of the forest. It can be palms, it can be lianas, it can be tree architecture. Some ecologists have started to look into this, and I think that is extremely important, for example, to link these architectural shapes that we can actually get today through the use of terrestrial laser scanning, but also liana infestation into our understanding of how fpar changes. So this is my ideas in very short, in 25 minutes. I want to thank NSERC at the University of Alberta and IBM for all the support that can give us over the years. And I don't know if we have some time for questions, but it will be great. Thank you very much. Appreciate it.